everyone. Thank you for the intro.
Yeah, great. Thank you for being here at the university. So the floor is yours.
Thank you. Let me share my screen. Okay. Hi, everyone. I'm Shruthi. I'm here to talk about fully homomorphic encryption today. This talk is based on our Communications of ACM article with the same title that went out in May. So a lot of it is about FHE, its compilers, and some latest updates that are happening in the world of FHE. So what is FHE? I'm going to talk about a little bit of an introduction of FHE, the privacy benefits it provides, how it works, and some of its challenges, and a brief history of FHE. And I'll do a deep dive into what I call FHE transpiler or compiler, and then a bit about HAIR, which is a foundation for FHE compilers, and I'll leave some time for questions. Okay. So what is FHE? FHE stands for fully homomorphic encryption. It makes computation on encrypted data possible. What does that mean in privacy terms? In the current world, we have secured storage and secure communication, but not secure computation. For example, take some form of an email server. When you send an email, it gets encrypted on your phone, gets sent to the server, where when it's stored, it is encrypted. But if some enhancements are happening on the email, like spam detection and etc., it usually gets decrypted during computation. And then the result of that is again encrypted and then sent back to the server. So when the computation is happening, the data stays decrypted. That means it's vulnerable to some attacks. So to prevent these attacks, for example, we could turn end-to-end encryption. You probably have heard of WhatsApp end-to-end encryption, messages end-to-end encryption. But as soon as you turn on this end-to-end encryption, the server loses the ability to do these enhancement computations, just spam detection, and maybe running some machine learning models to give you more features. So with FHE, you can do those computations on the server side. That means you'll still be able to provide the features that are needed for the clients of your product. So in providing these privacy benefits, FHE prevents insider risk, meaning it prevents internal employees from accessing user data. It ensures policy compliance and data minimization. Both of those roughly mean that we need to give data access to the fewest jobs and fewest people possible. So how does FHE work? The concept of fully homomorphic encryption states that for any function f that you can perform on the plain text, which is like the bottom, you can perform the same function in the ciphertext space, meaning that once you encrypt it, you will still it's no longer gibberish. It's gibberish in a way that you can still perform some computations on it. So so mathematically, it relies on a hard problem. Usually in cryptography, to give privacy, you rely on hard mathematical problems. So one of these hard mathematical problems that fully homomorphic encryption relies on is learning with errors problem. It's a very small, brief introduction. So learning with errors problem is a lot like solving a system of linear equations. So given a blue matrix and the green vector, can you find the red secret? And this is simple. You can just do a Gaussian elimination and you can find the secret. But if you add small noise strategically, then it is conjectured to be a hard problem to solve, even with quantum computers. So this is post-quantum cryptography as well. So using this learning with errors problem, we encrypt our messages. How? Using this noise. Basically, if you have your message which interplays with the noise well, then privacy is preserved. And so you get encryption with LWE in this way. By the way, these are pi-world problems. In reality, the matrices are huge. They are like thousand by thousand size matrices. So as you start thinking about computing on encrypted data, you are actually working on the real world huge ciphertext space, not on the toy world plaintext space that we saw. Okay, so it sounds great, magical that we can encrypt with LWE, but it has a few problems. So as you do computations in the ciphertext space, and imagine each of these bars as one ciphertext, it has message, it has error. Error is nothing but the noise. As you do computations, not only the computation applies to the message, but also to the error. So as you do more and more computations, the error grows. And if it grows beyond a point, it corrupts the message that you can never retrieve it back. So that's one of the biggest challenges of FHE, is what to do with the noise. So you can do what we call noise management, either by choosing large parameters, meaning make those large matrices even larger, so you can fit your entire computation, so both the error and the noise can still coexist. Or the another solution is you can track your noise and perform what we call periodic ciphertext refresh operations, which are very performance intensive, which reduces the noise, like you see on the bottom one, to a lower level so you can still continue to perform more computations. So there's a lot of bells and whistles that are happening when you try to develop FHE programs. So those big challenges can be divided into two categories. One is how to use FHE. Sorry, was there a question? Okay, I'm going to continue. So one is how to use FHE because of all of the ciphertext management that you need to do. And also because speed is because the computational encrypted are very, very slow because you're performing on these high dimensional ciphertext space. So I'm going to focus a lot on usability in this talk. So FHE programming usability means that we need to abstract away cryptographic details from engineers. So there are two subcategories of these FHE programming challenges. One is cryptographic and the other one is engineering. Cryptographic challenges are something that I think you must have got a bit of intuition because of the noise management. You need to know how deep your circuit is, so how many computations you're performing. You need to be able to track noise. Bootstrap is the ciphertext refresh operations that I just talked about. So you need to insert periodic ciphertext refresh operations, and you need to choose parameters that are always optimizing for performance while still preserving privacy. Because if you don't choose large enough parameters, then the privacy is not preserved, because then the ciphertext becomes vulnerable to attacks. Okay, coming back to the programming challenges. Think about this a little. You're computing on encrypted data, so the server doesn't know what the data holds. So if my if condition in my program depends on a data that is encrypted, how will the server know which side to branch, whether to return A, whether to return B? You would have to rewrite all of your if-else conditions, and like it is written on the right. You have to have a condition which multiplexes between both the results, such that both branches are computed, and the branch that we don't care about gets zeroed out or multiplied by 0 based on the condition, and only the branch that you need to be returned gets returned. And by that same logic, how will the server know when to end a loop if it doesn't know what the loop variable is? And that still adds more overhead as you think about branch and bound optimizations. None of those optimizations work. All graphs are pretty much fully connected graphs because you would have to execute both branches. So branch and bound optimizations don't exist anymore. And the fourth one is using the right FHE scheme for the right FHE computation. Let me talk about that in a minute when I talk about the history. So let's take a trip down memory lane with FHE. Sometime before 2009, FHE was thought to be this magical technology that was not possible, that you could either do multiplication or you could do either do addition, but not both in the ciphertext space. So by the way, if you can do both addition and multiplication in the ciphertext space, that means that you can do any computation. That is why it is called fully homomorphic encryption. If you can do only addition or only multiplication, it's called partially homomorphic encryption. So in 2009, Craig Gentry came up with a thesis where it was theoretically proved that you can do both addition and multiplication, and you can perform these ciphertext operations through this bootstrapping method that we talked about a little early. But it was really, really slow. It took 30 minutes to perform a single multiplication. And that it was considered impractical at that point. Theoretically possible, but impractical to be implemented. Over a period of time, a lot of new develops happened between 2009 to 16. And I talked about the learning with error problems. There's a ring learning with errors problem that this is one of the slides by Chris Picard, which is a more optimized way of doing FHE using polynomials. You can pack more messages, it's more optimized. So in addition to this ring LWE schemes came a lot of FHE schemes. Now, what is an FHE scheme? FHE scheme is largely how you pack your messages and errors in your ciphertext space. And don't worry about these like acronyms. They are largely author names, not much functional meaning in them. So there were different FHE schemes that came into being based on how these messages were packed and how certain operations were optimized. So with the first one, you could do gates, meaning AND gate, OR gate in optimized way. With BGV, BFV, you could do integer arithmetic. You could do vector and integer arithmetic. With CKKS, you could do approximate fixed point arithmetic more efficiently. Mind you, when integer is optimized, it's not as optimized for gates. So the schemes, each of them were good at certain type of operation. Okay, so I'm going to talk about two big schemes that are largely useful, that are largely popular in the compiler world. The first one is the CGGI scheme, where gate operations are faster. So in the evolution of performance of FHE, it went from 30 minutes for single multiplication to a one AND gate in 10 milliseconds. There was one big breakthrough. At the same time, there was another world which was performing arithmetic computation, meaning you can do vector multiplications and machine learning, data science sort of applications. So that was until 2016. And from 2016 to 2018, we started thinking about doing more and more involved computations. There were compilers. Two popular compilers come to mind. One is Concrete Compiler, which was a compiler developed for machine learning using the PFHE or CGGI scheme. And one was Crypto Lab Compiler. Both are still popular compilers in today's world. And both of them were developed for ML. So coming to what I'm going to talk about today. 2021 is when we released FHE Transpilot. We saw a gap in general purpose compiling in FHE. So what we open sourced was a TFHE compiler for C++, so you could compile C++ programs. And I'm going to talk a lot in detail with C++. And in roughly around June of this year, we released a crypto system called Jackside, which can work on CPU, GPU, TPUs. And also KU Leuven or COSIC KU Leuven released a hardware accelerator for FHE using FPGAs that is more performant than AND gate of 10 milliseconds. So what we realized at this point was whatever compilers we have developed so far are optimized for CPUs, are good at algorithmic optimizations and cryptographic optimizations, but not so much when it comes to optimizing for hardware accelerators. So speed is one of the big challenges in the FHE space. So in the future, there's predictions for ASIC chips to be developed by 2025, where we expect 10,000x speed up of these ciphertext computations, at which point FHE will be as fast, almost just 10 times slower than plain text computation, at which point we can start thinking about deploying them in products. Okay, so my today's talk is going to be a lot of detail of the FHE transpiler and what we are doing with our newest initiative, which we call HARE, which is a foundation for developing FHE compilers, keeping in mind both all of the research that has been done so far, but also making it useful for compiling for hardware accelerators. Okay, so FHE transpiler, this is open sourced. That's the GitHub link if you're interested to take a look. All right. So the goal of FHE transpiler was this. Take any program that you write on plain text and be able to convert it into a program that works on ciphertext. So on the left is sum of two integers, on the right is the same thing, but it's happening in ciphertext space. By the way, the right one is n-bit full adder. And we use full adder because we know that in the TFHE scheme, gate operations are optimized. And also, what does a transpiler mean? A transpiler usually converts high-level language to another high-level language. You must have heard of like JavaScript transpilers or Java transpilers, which convert Java to JavaScript or JavaScript to Java or any other languages. FHE transpiler converts code that works on plain text to a code that works on ciphertext. So that's why we chose that name. Okay, and then I'm going to go a bit about the different layers of FHE transpiler. So the biggest thing that we wanted to keep in mind when we develop transpiler is to make sure whatever modules we are developing are modular, meaning that an expert can develop the specific optimization that they want to develop, interoperable, that if you optimize for one thing, you'd be able to use it with the rest of the parts of the stack. And they're reusable across schemes, across hardware. And I'm going to go over all of these one by one. Okay, so let's go back to our plain text program. Well, this is a very simple string capitalization program, which says that if my previous character is a space, then capitalize the current character, otherwise don't do anything. So the first part of the transpiler architecture is a parser. Remember that data independent programming problem that we talked about, how does the server know when to end a loop? We need to enforce that loops have static upper bounds. So XLSCC is one of the parsers which applies high-level synthesis. Now, this is an interesting coincidence that we found, is that even in hardware acceleration, hardware programming, static upper bounds is enforced. So we reused some of those hardware tooling to convert our program into intermediate representations. And the intermediate representation that we are using here is called XLS-IR. XLS stands for Extensible High-Level Synthesis. IR is intermediate representation. What intermediate representations help with are modularity and interoperability, meaning if you take a Python program and convert it into XLS-IR, you'll still be able to run the rest of the stack. So you wouldn't have to like build everything else from scratch for Python or for TensorFlow, for example. All right, so this is what the intermediate representation looks like. And then we need a way to optimize that intermediate representation. Because we are using these hardware intermediate representations like XLS-IR, and netlist IR, by the way, is another intermediate representation, largely Verilog based. Because it is Verilog, we were able to use state-of-the-art Yosis ABC optimization, which usually reduces the circuit or the computational graph almost by 40 to 80% all the time. Okay, so now we have our plaintext program. We converted it into a combinational circuit. We optimized it to the minimum possible program. The next part is called execution engine. Now, in traditional compilers, execution engines usually take that optimized circuit and run it on CPU, GPU, what have you. But in the FHE world, execution engine is not actually running AND gates directly. It's actually running ciphertext AND gates. So what the execution engine does, we can think of this as a scheduler, basically take these high-level operations and run these cryptographic operations on them. And this is the rewrite of that code. So on the server side, it would run the code to do computation on the ciphertext space. On the client side, it would give you a way to encrypt your plain text messages into the ciphertext space, meaning encrypt your integers, encrypt your classes. And this is very powerful because converting every bit, every data type, meaning like integers, floats, or basic data types. But if you start thinking about data types, that user-defined data types, classes, they can get more and more complex. And if you want to encrypt those, it's kind of very hard to do all of the bookkeeping. So the transpiler does all of the bookkeeping for you. And that's one of the other features of the transpiler, is that you write your C++ code using your plain text code, using your general purpose code, and then the encryption, decryption, the client side and the server side is kind of taken care of for you. Okay, so I said that these are circuit schedulers. And this is a very interesting, this is my favorite part of the transpiler, is how do you schedule these cryptographic operations across different types of hardware? The simple single-threaded scheduler just executes things one by one. That's easy. Multi-core, when you start thinking about multi-threaded scheduling, then you start thinking about what are the parallel parts of your graph. And you can execute them first, you can execute them next. But then that doesn't apply for GPU. GPUs work for single instruction, multiple data scheduler, meaning that all operations of the same type need to execute at once. And TPU is a completely different ballgame. It's single program, multiple data scheduler. It's like SIMD, but not quite. And so there is high performance computing and computer architecture and distributed systems as well. What if you have multiple hardware multiple, some CPUs, some GPUs, can you use them together? How you're going to do the memory management, because these ciphertexts are huge, and how you're going to move your ciphertext across these devices on your distributed system. These are all interesting problems that pop up in this space. So what these circuit schedulers doing are actually just calling out cryptographic functions from these libraries, which tell you to perform an AND gate on ciphertext, perform a multiply on ciphertext. But that's not, but there is still a job to be done on the compiler side to convert those into actual machine learning, machine instructions. And that's where this math hardware layer and hardware accelerator layer comes in. This is the bottom of the stack. So this means that we need a way to accelerate these cryptographic primitives, which has a lot of intricate math involved in it. A lot of that math is polynomial math. And how do you maximize the performance on different kinds of hardware? That's a very open challenge in the FHE space, because the type of the instructions that FHE has are completely different. And one of the more important thing is benchmarking. What do you mean benchmarking across hardware accelerators? So in general, in hardware accelerator world, you can take an operation and give a number of maximum parallelism possible. But programs are not almost 100% parallelizable. So the program runtime is usually slower than the maximum possible runtime usually. So we need a way to benchmark across just the primitive instruction level, but also at the program level to be able to say how fast can you run, say, your machine learning model or say your C++ program. Okay, and that kind of comes to an end of the FHE turns pilot. Those are all the parts of the stack that we needed for C++ compilation using Boolean gates. There are some, check out the GitHub repo that was shared before. There are some cool examples of email spam filtering and some games that people have tried. And it's very interesting to see what C++ programs folks have developed in FHE. And so next is we want to expand this to also support arithmetic like private ML inference, private machine learning. Now we need more things that that will complete the FHE, what we call the FHE stack that we are in the process of developing. Now, I added this new module, which is called FHE architecture selection module. So far, I have assumed I'm only going to do AND gates, but right now, with machine learning, I want to do more involved arithmetic computation. So architecture selection, meaning what are the parameters? What scheme do I want to choose? How do I encode my message in one of those schemes? All of those become new questions in the private ML space. So the big blocker to FHE is, see those purple things where IR is marked, is the intermediate representations. The intermediate representations so far we have used are hardware-based. They don't support modeling noise. They don't support all of these cryptographic new things that we need to optimize for. So the extensible intermediate representations are the biggest blocker to the FHE stack. So we started the effort called HEAD, which is Homomorphic Encryption Intermediate Representation. I'm going to give you a small glimpse of what HEAD is and then leave you questions. So what is HEAD? HEAD is a compiler toolchain for FHE and more. It allows you to do, it's also a benchmarking platform. So it allows you to benchmark across operations, across hardware, across operations, across many levels. And I'll talk about that in a minute. HEAD is built with LLVM's MLIR framework. Okay, one more acronym. What is MLIR? MLIR stands for Multi-Level Intermediate Representation. It's a collection of modular and reusable components. And this is important, that enables progressive lowering of operations to target hardware. It was actually built for TensorFlow, but we realized we can just as easily use it for FHE. And a lot of researchers in FHE have already been using MLIR. So it's a great fit because it has multi-level abstraction. It is not opinionated, that it does not restrict you to use only one type of operations or one level of abstraction. And it is very modular and extensible. A brief, small intro to MLIR, just to give a sense of why MLIR is the best fit for FHE compilation. So MLIR is like an intermediate representation. It's like a language that allows you to represent any operation. So there are variables. That's true to any language. There are operations, and there is on the top there is static typing. So you can define your data types, there on the bottom are the two big things. There is user-defined custom syntax, but there's also dialects. And dialects is where the power of MLIR lies for FAG. You can define dialect at different levels, and each dialect has its own operations, and you can go between dialects. And so that's what we're working on in here. It's very unfinished. We've just started this initiative. So each level can be thought of a different type of dialect. Each box can be thought of a different dialect here. There is your Python, ClangIR, CIR, PolyGuys. These are some of these front ends. And you can convert that into your dialect, which we call the secret dialect, where some of the variables are encrypted. And then you can define your own dialect for the next stage, which is all of the FAG schemes that I've mentioned. And then you can convert that dialect into polynomial dialect. And then the next layer, which is accelerator dialects. And if I want to leave you with one thought, is the goal for here, which is to build a compiler toolchain with all the established ideas in FAG to accelerate FAG research and lower the barrier to production FAG. So we are using MLIR framework for compiler toolchain. We want to develop these dialects so we can actually make use of all the existing established ideas. And so the framework allows you to actually focus on your novel ideas and not get drowned in rebuilding compiler parts while you're developing FAG. And then production FAG. Production FAG requires benchmarking and being able to say how much overhead does adding FAG to your application bring. And that's also one of the things that this compiler toolchain helps with. So we are also like trying to support more front ends, not just C++, but also Python and TensorFlow, and integrate them all at one place. All right. So we have a working group. We have an open design meeting every 2 weeks. If any of this interests you, we have participants from across industry, Google, Intel, startups such as Zama and Cryptolab, and universities and hardware startups. And as you can see, FAG is in this like very interesting space where it's a combination of compiler research, cryptographic research, as well as high performance computing all happening at the same time. And it's such an exciting time to be in FAG because it is where machine learning was 10 years ago, just coming into the realms of possibility, and compilers are what are missing, and that's what we're hoping to build. So FAG can be used as a privacy tool by any products. And thank you. This is our GitHub repo for here, and we have a working group. And I will open the floor for questions.
Thank you, Shruthi, for the great presentation. I think your tone and the pace was perfect. And I think it put all our listener to a very great listening mode. So I appreciate for taking and explaining the complex concepts such as FHE. And now it's open for Q&A. Yes, we have multiple hands raising up, so a lot of high school students are raising the questions. So go ahead.
When it comes to the hardware accelerators and the fully homomorphic encryption, wouldn't it be best to use an ASIC because it's a custom chip designed for that process?
Yes, I think yes, you're absolutely right that ASIC chips probably is going to give best hardware accelerators speed up. But bear in mind that FHE is such in rudimentary stages because there are so many schemes. ASIC chips are largely application specific chips. So unless we know exactly what kind of FHE scheme, what kind of FHE operation we want to perform exactly, it's hard to develop an ASIC which is programmable. So we're kind of in that phase right now, because once you develop hardware, you're stuck with it, right? Because it's not like software that we can go and modify it. So if we build a bunch of ASIC chips, we are stuck with it. Right now, there are a couple of programs. There's a DARPA program, and there's a couple of like universities and startups that have started building those ASIC chips. It takes 6 months to 2 years to actually like print a hardware chip. And then until we print it and run it, we don't know what challenges would pop up. So though that's kind of the ASIC chip scenario right now. It would be the best, but it just takes time.
Great question. Next question.
I was just wondering if this was going to be integrated into messaging services like Gmail, because there's already like encryption strategies being taken, but would this be better than some of the things that are already implemented?
So far from the messaging systems that have started end-to-end encryption, I do not know of any which supports any of these computation on encrypted data yet. And please, if anyone knows, correct me. But FHE is slow. The other alternative technology that you could use that is somewhat in the computation on encrypted data world is secure multi-party computation. But again, that adds network overhead in a different way. So there are different challenges. And for real-time messaging, I don't think FHE is there yet, unless some hardware accelerator pops up with lots of speed up.
Thank you for that
Thanks for the
question.
question.
Sikong.
Hi. So FHE is very, very interesting. So I have a question related to security. So what will happen if the high-level code you convert to work with FHE has some serious vulnerabilities, such as signed and unsigned integer bug, format string vulnerability? So would it be possible to exploit FHE, through putting some malicious code for converting, or does FHE implement any strategy to do some input validation? Yeah, that's my question.
There's two parts to that question. I guess, like, just to repeat your question that you're asking, will you be able to inject some data, inject some malicious program, and then get other information from the server than what you want, which is execute malicious code on the server? And also, can you leak information through FHE programs? The thing with FHE computation is everything on the server will run on encrypted data. So even if your data tries to run something and access some other part of the code, unless it is allowed prior, it will not be able to like expose anything to the server. The threat model that we are considering here is we don't want to reveal any user information to the server. So server will not be able to see anything that anything from the user that it's not supposed to see. The second question, will FHE guarantee that the computation that the server needs to perform is the computation that it is performing? No, FHE does not guarantee a malicious server. It assumes that server does what it's supposed to be doing with the data, meaning that can FHE always predict the wrong result? Will you be able to know? Is it doing the right type of computation? We need to enhance it with something called zero knowledge proofs to give you that extra guarantee. I don't know if the second question is what you asked, but that's another adjacent technology to FHE that you can use.
Great. Any other questions? Okay, if not, let's thank Shruthi for her time. Thank you, Shruthi, for giving your time for UND's CAR Symposium. As part of a token of small appreciation, you will receive a plaque from UND. Thank you again so much.
Thank you. Thank you for listening.